So I'm not getting any audio from you, just so you know. Oh, you muted. That's fine. That's fine. Just making sure.
All right, so welcome everybody. In principle, everybody should be able to hear me. The people in the room, hello. The people on Zoom, hi. And then the people on the streaming, hi. And, so today it's my pleasure to introduce Ricardo Schiavon, who did his PhD in Sao Paulo and then via way of the USA and Hawaii came to the UK and is now a reader at Liverpool John Morris University. So he's an expert in galaxy formation, but lately he's been moving towards our own galaxy using large spectroscopic stellar surveys to understand the Milky Way. And today he's going to tell us what he's done with that using APOGEE and to study the inner halo. So I'm going to do everything I'm supposed to, and Ricardo, you can then share your slides. We can no longer hear you.
Right. So before sharing the slides, I would just like to say a word of thanks to you folks for this invitation. It is an honor to be talking here. Talking there in virtually today. Giving a colloquium in Cambridge is the kind of thing that you tell your parents, right, over the phone. So, which I did on Sunday. I'm going to give a seminar at Colloquium in Cambridge. So it's I'm very pleased to be here and appreciate the invitation. So now I can share the screen. So I'm going to be talking today about the inner halo of the Milky Way. And by inner, I mean really inner halo of the Milky Way, the inner few kiloparsecs of the halo of the Milky Way. People usually, when they talk about the inner halo, they're talking about something like within 10 kiloparsecs of the galactic center. But I'm really focusing here on the inner halo of the Milky Way. So I will hover over quite a few results, and so I'll have to do that in a pretty high level without descending much into the details. But please, by all means, either interrupt me or ask me any questions that you might have about the details of what I'm talking about here. Okay, before starting, I would just like to say a word of thanks to the many people who are making this work possible. Science now, these days is teamwork, and I have been blessed by great grad students, great postdocs in the fabulous APOGEE team. I would like to highlight here Danny Horta, my fourth year PhD student. So he's in the job market now, and a lot of the work that I'm going to talk about here today has been led by him. Okay, so what I'm going to talk here is, I'll start first by giving you a raison d'etre of galactic archaeology, why exists, what are the goals, what is the remit of galactic archaeology. Then I'm going to try to motivate here why we care about the halo and why, in particular, the inner halo. And then I'm going to briefly describe APOGEE and then talk about the main two discoveries that were made possible by this survey, and then address a fundamental question about the unicity of the Milky Way, and then conclude. Right, so part one, then galactic archaeology. What is galactic archaeology? Galactic archaeology is a field, a branch of astrophysics that deals with the following questions. Number one, what is the current structure of the Milky Way? And by structure, I'm quoting structure here because we mean not only the spatial distribution of the matter in the Milky Way, but also the distribution of the stars in particular in multi-parameter space, including obviously the spatial structure itself, 3D kinematics, and chemistry. So once you have been able to map that structure, and there are a number of surveys being undertaken today to perform that task. The next question then is, what is the history that led up to this structure? How did the galaxy come to be this way? What was the physics that was responsible for the current state of the galaxy? Next question, once you have been able to devise satisfactory answers to these two questions, is what does that teach us about galaxy formation in general, if anything? And that latter question is obviously, in order to address that latter question, we need to be able to first devise whether the galaxy is typical. Why? Well, there are two reasons why you want to know whether the galaxy is typical. Number one, we live in it. So understanding the genesis of the galaxy is understanding our own genesis. Therefore, understanding our place in the universe involves knowing whether we live in a common galaxy or not. But that is in the narrower context of galaxy formation theory. In order for you to use the Milky Way as a template to understand galaxy formation, you want to make sure that it's a common galaxy. Otherwise, any conclusions that you derive from the analysis of the extremely detailed data that you obtain for the Milky Way becomes difficult. We can't just extend these conclusions very easily, because if it's a rare system, then generalizations are made difficult. So every talk about galactic archaeology starts by saying, well, the Milky Way is the galaxy that we know best, or for which we have the most detailed data. Therefore, it can be used to constrain a galaxy formation theory. Well, let's be careful about this. It can be used very easily if it is a common galaxy. If it's not, then the generality of the conclusions that we arrive to from these studies should be called into question. Right. So now, why do we care about the halo of the Milky Way in particular? So, in particular, because of the accretion history of the Milky Way, which of galaxies in general, which is the accretion history is an important consequence of lambda-CDM cosmology, and is a very solid prediction from cosmological numerical simulations. Right, you start from the quantum density fluctuations, let gravity do its work, and you pretty much infer an accretion history, in a quite straightforward fashion. So it's a strong prediction. And we do observe, in the galactic halo, in crystallized form, the fingerprints of those accretion episodes, right? And here you see a very famous paper by Vasily showing the field of streams, revealing the presence of streams related with various accretion events. Back in 2006 using slow data. And then here on the right, you see similar signatures of accretion events in the case of Andromeda, conducted by Rodrigo Ibata and collaborators. So The bottom line then is that we can use observations of the halo in order to retrace the history of accretion of the galaxy. Now, pictures like this, right, would suggest that the job is relatively simple. And you know, for the outer halo, that is true, and for relatively recent accretion events, that's correct. However, if you want to detect early accretion, right, then you just positions in substructure, spatial substructure, is not enough. You need Gaia and you need spectroscopic surveys to help. And since the advent of Gaia, lots of substructures have been detected. There's a number of them listed here. I'm just going to highlight a couple of discoveries made in Cambridge. You know, first one in the pre-Gaia era, the discovery of the Sagittarius dwarf, which is currently being engulfed by the Milky Way, spiraling into the galactic potential of the Milky Way. Discovered from radio velocity studies towards the bulge. It's far beyond the bulge, and so the detection was quite difficult. And but nowadays we have traced the streams of Sagittarius pretty much across the sky. And then the much more difficult detection, which is that of the Gaia sausage made by Vasily and collaborators, which is shown here in the form of a system with a very large scatter, very large dispersion in radio velocity and very low dispersion in azimuthal velocity, which is therefore deemed as the sausage, which has been now then hypothesized to be, or pretty much demonstrated to have been, an accretion event that happened in the history of the Milky Way over about 90 years ago. But we in Liverpool have ourselves detected the presence of Gaia enceladus sausage in the APOGEE data. You can see here the plot showing the alpha over iron abundances ratios, right? So against metallicity, right? And so what you see here is the stars. This is called by eccentricity. The stars with highest eccentricity tend to have lower alpha over iron for a given metallicity, and that's a signature of a star formation rate that was low, which is characteristic of systems of low mass. Okay, so now all of this is, I'm talking here all about detections made in the outer parts of the halo. However, I would like to call your attention to the importance of the inner parts of the halo within a few kiloparsecs of the galactic center, as I said before. First and foremost, roughly half of the halo mass is located within a few kiloparsecs of the galactic center. So this is like very back of the envelope calculation. You get the density profile from, for instance, Iorio et al. And you just integrate that over a given radius, out to a given radius. And you get a very simple function. I'm here ignoring deviations from spherical symmetry, and you get that roughly a half of the halo mass is located within the inner few kiloparsecs. So in this case here, if you integrate out to 3 kiloparsecs, that's half of the mass that you get if you integrate out to 30 kiloparsecs. And you see here two density profiles that were inferred by Danny in a paper studying the density of the halo stars in the APOGEE data. We'll go back to that plot later. Right, so this is number one. So most of the mass of the halo is near the galactic center. Second, if you want to detect the earliest accretion events, which are driven, you want to go to the inner parts of the galaxy because they are driven there by dynamical friction. This is here the results of a simulation using the Latte suite of simulations. This is from 7 Milky Way-like galaxies. This is also work done by Danny in collaboration with the FIRE team. And what you see here is the energy normalized by virial energy as a function of the time of infall, the energy of satellites that were accreted by these Milky Way-like galaxies in the simulations, right? And so as you can see, and it is a color-coded by mass, and this is the mass that the system had just before crossing the virial radius. And you can see here that the earliest accretion events taking place 10 gigayears ago they tend to be concentrated at low energies, right? Therefore, very close to the galactic center. And so if you want to detect those systems, you really need to investigate the inner parts of the galaxy. Third, and also very important, the oldest stars in the Milky Way reside there. And this has been demonstrated over and over by numerical simulations by different groups. So I have no plots to show about this here. But the important thing here to keep in mind is that, okay, great, within 2-3 kiloparsecs of the Milky Way, we have all this treasure trove of information that we can try to glean and to understand the early history of the Milky Way. However, we are talking about the inner 10, 15 degrees off of the galactic center, which, as you know, is what we call the galactic bulge, and that's characterized by very high extinction, so hard to access. And on top of that, the metal poor populations, the halo populations, are vastly outnumbered by the far more numerous disk and bar populations in that region. So, and that's where APOGEE comes. So APOGEE, I'm going to very quickly describe APOGEE here. It's a survey, dual hemisphere spectroscopic survey of the stellar population of the Milky Way based in the near infrared. The telescopes used here are the 2.5 meter SDSS telescope on the left. On the right here, the Dupont Las Campanas telescope. The PI of the survey, Steve Majewski. This summarizes the main characteristics of APOGEE. The technical characteristics of APOGEE is based on two twin spectrographs with 300 fibers multiplexing each at high resolution in the H band. Right, and we are talking about high precision spectroscopy. I'm not going to go into much detail here. What I want you to take home about APOGEE and why APOGEE is such a water divisor in the history of galactic archaeology is that it's a high resolution survey delivering spectroscopy at a relatively high resolution, 23,000 in high signal to noise, which means that you can derive precision abundances for a very large number of elements in the same style as was done by hand by generations of astronomers in the past. And you do that in the near infrared so that you can reach every direction in the galaxy. And you do that for 700,000 giant stars, which allows you to see far. Okay, so that's basically what makes the difference for APOGEE. So I'm just going to synthesize the information from APOGEE in this plot here. You can see here, I selected, pardon me, over 300,000 stars with in a range of temperatures and surface gravities and signal to noise where you get precision abundances for various elements. This is just a small sample of the elemental abundances APOGEE delivers. And you can see here in various planes that there is a lot of structure here. This is the entire sample. I didn't select stars other than by selecting by temperature and surface gravity and quality of the spectrum. Now, if you squint, you realize that there's lots of structure here. And for instance, the sausage can be easily seen in all planes. Right, the Gaia sausage, you see the Magellanic Clouds are located here. They are more easily distinguished here and here. You can see Fornax, you can see Sagittarius Dwarf, you can see the thick disk, another contribution by Cambridge to our understanding of the galaxy, the thin disk, and so on. So this shows you that the chemical compositions that we are providing here, they encode different histories of star formation and chemical enrichment, and which we are still working hard to try to understand what they are teaching us, okay? So, most importantly for this talk, and APOGEE is making a big difference in providing for the first time detailed chemistry. I'm talking about up to 20 elements, right? For 10,000 stars, roughly, within 3 to 4 kiloparsecs of the galactic center. And that is unprecedented, never has been done before. And every time that you do something new, that you expand your observational horizons, you find something new in astrophysics, pretty much. So if you combine that with precision distances, right, based on Gaia, you have a powerful tool. Okay. So then the transition is now from this huge sample that I showed before to a sample within 4 kiloparsecs of the galactic center, and you see that this transition here already contains a lot of astrophysics that is we are scratching the surface to try to understand, right? But my focus here today is going to be on these, the nitrogen-rich stars that you've seen here, which have globular cluster kind of chemistry, but are actually field stars and are not in globular clusters, and Heracles, which is a building block of the galactic halo that we think we have discovered within a few kiloparsecs of the galactic center. Okay, so let's talk about those discoveries then. First, let's talk about dissolved globular clusters. This is a result that's no longer new, but we are trying to put this into new context now. So back in 2017, when we took a first look at the APOGEE data, focusing on the abundance of carbon and nitrogen and other elements, but mainly carbon and nitrogen, we flagged a population of stars in the galactic center, in the region within 2 kiloparsecs of the galactic center, that had chemistry that was characteristic of stars that we knew to exist in globular clusters. Only they were in the field, they were clearly field stars. So let's zoom in a little bit here on this plot and see that in more detail. So what you see here is nitrogen abundance against carbon abundance, right? In the top panel, the bulge field stars are these gray dots here. And then we flag these high nitrogen stars, which are marked here with these bigger symbols. And in the bottom panel, you see stars from globular clusters, right? A family of globular clusters here in a range of metallicities that span a very large range of nitrogen abundances. So this is being interpreted and not understood completely as a generational phenomenon within globular clusters. People have proposed that this first generation, these stars that have abundance patterns that look like those of the bulge of the field, they are first generation stars, and the other ones that have abundance patterns that differ from that of the rest of the field stars, they will be second generation. As a matter of fact, we don't really know how globular clusters produce this. There's no model that accounts for the data in its full. So this interpretation is actually subject to questioning. But what matters for us here is that we are using globular clusters as taggers. We're just trying to use them, these populations, to tell what happened with globular clusters that once existed in the galaxy. So if you look at the metallicity distribution of these stars, again, these nitrogen-rich stars that have second generation abundance patterns but are in the field, look at their MDF, and you see the MDF is in the middle panel. It is vastly different from that of the bulge. The bulge is characterized, of course, by several components. We'll see a little bit more about that in a few minutes. But most importantly, it differs beyond a shadow of a doubt with high statistical significance from the MDF of the galactic globular cluster system, both the entire globular cluster system and the clusters which are just in the bulge, which are shown here in gray. Which means that these stars do not come from the existing globular clusters. So our hypothesis is that they result from complete destruction of globular clusters, of a family of early globular clusters that don't exist anymore. Now, the implications for this are very important, because if you calculate the mass that is contained in these destroyed globular clusters, it adds up to almost 10 to the 8 solar masses, which exceeds by a factor of several the entire mass, so the mass of the entire existing globular cluster system. Okay, so this is not new in a sense. What is new is the discovery of these many stars in the inner part of the galaxy. People have detected in the past the presence of these stars in the outskirts of the halo, not outskirts, but 10, 15 kiloparsecs away from the galactic center. And this has been studied for a while, right? But the frequency of these stars in those regions was very low, 2.5%, whereas what we are finding here is much higher in the inner parts of the galaxy. So Danny then did the hard work of correcting the discounts for the selection function of APOGEE, fitting density models, and deriving the real, what is the density distribution of both the halo and nitrogen-rich stars, which you see here on the left. So this is the halo density law, which matches very well that inferred by Iorio and collaborators from Cambridge in 2018. And then this is the nitrogen-rich star distribution, which is, as you can see here, is steeper. If you take the ratio here, you see that the contribution of nitrogen-rich stars, of these cluster these remnants of cluster destruction in the inner parts of the galaxy can add up to 15% of the total stellar mass. Okay, now Shobit Kisku, another Liverpool student, did a different thing. He selected these stars that are located within 4 kiloparsecs of the galactic center and studied their chemistry, and found that in the same way as the plot that I showed you before of the detection of Gaia enceladus, showed that there's a fair number of nitrogen-rich stars in the inner galaxy. They have abundance patterns that are characteristics of accreted systems. In fact, he showed that about 30% of the nitrogen-rich stars in the inner part of the galaxy, within 4 kiloparsecs of the galactic center, have chemistry of accreted systems. Looking at their distribution in the energy, angular momentum plane, the integrals of motion, you see that they are mostly occupying regions of low energy bound to the inner parts of the galaxy. You can see here at higher energy, these stars here, which are not nitrogen-rich, these are right in the area where the sausage Gaia enceladus is. So these are stars that are just crossing the inner part of the Milky Way at high speed. Now, if you then just select stars in the APOGEE sample, this is stuff that is unpublished, it's still in preparation, preliminary. If you select, you get to the APOGEE sample and select stars that are chemically accreted. Okay, I will get to that definition. What is a chemically accreted star later on? Select them with chemistry of accreted systems, right? And this is the distribution that you have here again in the energy against angular momentum plane, right? So this is high energy, low energy, so unbound, bound, right? The positive angular momentum here is prograde, negative is retrograde. And this circle, this green circle here that you see here is where the sausage is, right? And the dark points here, the black dots are nitrogen-rich stars. These data are color-coded by silicon over iron. These purple stars here are all Sagittarius dwarf stars. You see that there's no stars there, very few nitrogen-rich stars, you know what they are. And so that means that these stars exist abundantly in the sausage. Another plot here showing, again, I have applied no kinematic selection here. This is selection purely chemically, right? So this is the standard azimuthal against radial velocity plot, and showing here the sausage and the nitrogen-rich stars clearly aligned with the sausage. Some of them are positioned here along with the high alpha disk. We can talk about those later. Okay, so nitrogen-rich stars exist in the sausage, but they do not exist in the Magellan clouds, in Fornax, in Sculptor, or in the main body of the Sagittarius dwarf. I'm not going to show plots of this because non-detection plots are boring. Okay, so summarizing then, what we found here is that there's this large population of what seems to be remnants of globular clusters, right, which were destroyed and are found predominantly in the inner parts of the halo. The mass adds up to 10 to the 8 solar masses, give or take. They are highly concentrated towards the inner parts of the halo, with 30% of their mass likely being accreted. You don't find them in dwarf satellites of the Milky Way, you find them in the sausage. So they seem to be associated with accretion. Okay, talking about accretion, second part, the second discovery, which is the galaxy within the galaxy. So what is this? So this is the press release picture that shows the spatial distribution of the stars that we discovered in the inner parts of the Milky Way, where they are. Obviously, this is not the real distribution of the stars belonging to this system. This is, of course, dictated by the apogee selection function. Okay, so how did we find this, and what does it mean? This is the parent sample that we're looking at now, a little further selected to make sure that we have only the best data. This adds up to 145,000 stars, almost in the right temperature range, signal to noise and metallicity. You can see here the clear high and low alpha, the thick disk and thin disk components here. This is this little smaller constant bump here, clump here is Gaia Enceladus. If you look at the distribution of this data in the integrals of motion plane, you see the main structures, right? So this most of the stars here are located in the disk, right? Some of them are thick disks, therefore they have they're thicker here. This basically for a given amount of angular moment, they have more energy, right? Meaning that they have energy towards a non-rotational component of the motion. You have the splash here that was discovered by Vasily and team a few years ago, and Gaia Enceladus, so Gaia Enceladus sausage again here. Now, if you look at these stars in this chemical plane here that has been proposed by others to select stars that are either accreted or in situ, where this part of the in situ is the high alpha, thick disk component, and this part of the in situ is low alpha, thin disk component. They have proposed that these stars here make up an accreted component. We have looked into this a little, more carefully, and we show in our paper that there is some contamination here from in situ populations, okay? But if you look at the data, the distribution is definitely clumpy. The red dots here, so I forgot to mention that the 2D histogram shows the parent sample, and the red dots here show the stars within 4 kiloparsecs of the galactic center, again showing a clumpy distribution. Right, so if you just show the accreted sample from that, so I'm just showing this component here, the accreted sample in the same integrals of motion plane, you see that it's clumpy, no longer characterized by those smooth distributions, and I'm indicating here, so there's with the red arrow, Heracles. The big clump here is Gaia Enceladus sausage, and there's a little bit of the splash here you can see as well. Okay, now we have done a lot of a very careful examination of this data, and we have compared the chemistry. We studied the chemistry of these cell populations and shown that they are detached. So you can reproduce these distributions in these planes by detached components which overlap, but are still detached, in the sense that in order for you to obtain this clumpy distribution, you have to have a crazy history of star formation, which is possible, of course, but it's more indicative of an overlap of structures that evolve chemically in separation. If you now select stars within these two clumps, just for comparison of the sausage in Heracles, imposing basically just an energy in this case and eccentricity cut, what you find is that the distribution in the various planes is different, in the sense that so while both have abundance patterns that are characteristic of systems similar to satellites of the Milky Way, they differ in detail. So in particular, the Heracles has a higher alpha abundance than the sausage, higher carbon nitrogen, and higher aluminum. Perhaps most interesting is the star formation history that you infer from just a very qualitative look at the data. You have seen plots like this before, where the distribution of a stellar population, you can see here clearly here in the case of the thick disk, right, it's characterized by a thigh or a plateau, right, and what is called a knee of the distribution, then a shin. This knee of the distribution occurs when the contributions by supernova type 1a, which enrich the interstellar medium in iron substantially, not so much in magnesium, when this contribution, which happens at a time characteristically between 100 mega years and 1 giga year, when that happens, then that's when the knee forms, and then the magnesium of iron starts declining. You can see that clearly in the thick disk. You see that clearly also in the case of the sausage. Okay, you don't see that in the case of Heracles. So our interpretation of this is that supernova type 1a did not have time to enrich the interstellar medium of this system before it plunged into the Milky Way, which suggests then that it was the victim of a very quick quenching of star formation associated with a very early merger with the Milky Way. Now, distinguishing Heracles from Gaia and Celadus is easy. As you have just seen, you can see, by just looking at the data, you can completely identify differences there. However, the real difficult part is to distinguish Heracles from the inner metal poor thick disk. And in our latest paper, which is going to appear in the archive before the end of the year, Danny now has compared in detail the chemistry of large samples and applying a chi-square approach to determine differences between different systems. So, for a good example here, at the top you see a comparison between Gaia and Celadus sausage with the high alpha disk, right? The different elements, and the differences are substantial. The chi-square is huge, right? So the probability that these two systems are similar is very small. Now here, and unsurprisingly, right, because we know that the sausage differs from the high alpha disk, as we have seen here, tremendously, right? So there's no question about that. Now here, we compare now Heracles with the high alpha disk, and the differences are also important, in particular in elements such as sulfur, titanium, carbon, manganese, and cerium. So from a chemical tagging point of view, we can distinguish Heracles from the in situ population that coexists with it within 4 kiloparsecs of the galactic center. So summarizing then what we have here, we found evidence for a remnant of satellite accretion within the inner part of the halo. This satellite accretion likely happened at Z larger than 2, large redshift, with a mass which we inferred through comparison with the chemistry from the Eagle simulations, which is twice that of Gaia and Celadus sausage, and making up a substantial fraction of the metal poor bulge. We examined other possible scenarios of this being part of the core of Gaia and Celadus sausage, or being just an in situ population, and we deemed those scenarios less likely. Now, the last part of this talk is aimed at examining whether this that you're seeing there is a common thing. Is this a common phenomenon in the universe, the galaxy we live in? How do we look at that? So the main observable here that we're trying to understand is this alpha bimodality that you see there. Again, magnesium over iron, magnesium an alpha element, iron peak element, obviously, sorry, this is metallicity here, producing a system that has, for same Fe over H, same iron abundance, 2 different magnesium over iron is extremely difficult on the basis of standard chemical evolution models. It requires a lot of juggling with free parameters. Now, if you think that's a problem in the solar neighborhood, consider the fact that it's everywhere. This is probably one of the most important results by APOGEE, showing that this alpha bimodality, and here is work by Hayden et al. 2015. So each of these panels here shows you a population within a given galactocentric distance along the plane and away from the plane in a vertical. So from 3 kiloparsecs to 15 kiloparsecs away from the center, and from on the plane out to 2 kiloparsecs away from the plane. And you can see here that the bimodality is, except for the very innermost parts of the galaxy, of the disk, it's pervasive, it's everywhere, it's ubiquitous, right? So, as I said, it's very hard to do that without resorting to adjusting free parameters. So what did we do? So Ted Macrith, Rob Crane, and I decided to look at the Eagle simulations and ask the question, do the simulations show galaxies with some kind of alpha over iron bimodality? And if so, what is the physics that causes it? Those are the two questions that we asked. So I'm not an expert on numerical simulations, so I'm going to very quickly run out of my depth here. So I'm just basically tell you that we focused on the 100 megaparsec box, right, which contains about 133 Milky Way-like galaxies. Those galaxies were selected to have the mass of the Milky Way, give or take, and the morphology of the Milky Way defined in terms of angular momentum, really. So, and then we just selected the disk parts of these galaxies and examined the chemistry of the populations. And so we find that there are galaxies with a bimodal-like distribution, or at least with a scatter in the alpha iron plane. And what we found is only 5% of Milky Way-like galaxies in Eagle show anything like a high alpha, an alpha bimodality. So one question is answered. So yes, the simulations do generate galaxies with that bimodality, but only 5% of them. Second question, what causes it? And after a lot of head scratching, what we found is that what causes it is the accretion history. These galaxies differ from the others, and this is a plot showing mass growth as a function of time, right? And the galaxies with bimodal are in red, and the galaxies with the other galaxies are in blue. And these 5% galaxies, they have a sudden growth in mass associated with a very active accretion history in the early stages of their lives. Okay, so, right. So the question then that we asked, is there a typical galaxy? Should be framed in the following context. When you ask if a galaxy is a typical galaxy, you want to ask whether the galaxy is a typical galaxy according to a parameter that is physically relevant to what makes a galaxy a galaxy. So the accretion history happens to be one such parameter. The accretion history of a galaxy is fundamentally responsible for the way in which the stellar populations of the galaxy are organized in the galaxy today. So, and as I said before, it is a fundamental prediction and a fundamental consequence of lambda CDM cosmology. Now, I want to call into question then this paradigm. Copernicus changed our view of the world when he found that, the sun was, the Earth was not the center of the universe. It could explain the orbits of the planets better with a simpler model, which places the sun in the center of the universe. A paradigm became fashionable for the past many hundred years. We've been assuming that we don't live in a special place. Our position must, per force, be one that's mediocre, normal, standard. So what I'm saying here is that that is an assumption, no more than an assumption, and that needs a physical basis, an observational basis. an empirical basis. And we are providing here a first look at that problem and providing indications that perhaps, just perhaps, we do not live in a galaxy that is very common. It differs from its Milky Way-like counterparts at the 2 sigma level. Okay, so to conclude then, so I showed you here that when you analyze the largest ever sample of precision detailed chemistry and 3D kinematics of cell populations within 2 kiloparsecs, 3 kiloparsecs, 4 kiloparsecs of the galactic center, you find, number one, that there is a population of seeming globular cluster remnants that exceeds in mass that of the entire globular cluster system. That population seems to be associated with accretion because it's not found anywhere outside the galaxy, in none of these satellites, but it is found in the sausage. We also found that there is an indication of a major building block of the galactic halo buried within 4 kiloparsecs of the galactic center with a mass which exceeds that of the sausage by a factor of 2. So, and we also found in agreement, qualitative agreement, and hopefully in the future we'll be able to verify whether this agreement is quantitative, that the data that we have for the chemistry of our disk suggests that the Milky Way has indeed undergone an accretion history, which was very intense in its early times and more calm in the more recently. And so I hope that with this knowledge, we can go the extra step and obtain more data, expand the sample of chemistry and kinematics in the inner halo by a factor of 10 with upcoming surveys, SDSS 5, moons, and hopefully address these questions to satisfaction. Thank you.
Thank you, Ricardo. This is very exciting. So people in the room and on Zoom can ask questions. Streaming people, you can't. If you want to, then you have to join the Zoom. So on Zoom, well, and in the room, if you have a question, please raise your hand. Shall I kick things off? So I was wondering if there's any observational biases that can come from the fact that you use APOGEE, which really only looked at giant stars, of course, and if there's any observational biases that you are not taking into account that could alter your results.
That's a difficult question. Because if there were any, we would not have published this. So we did examine various observational biases. For instance, in the case of the nitrogen-rich field stars, we checked for radial velocity variations. Are these transfer binary, stars, for instance? Are they AGB stars? Do they have AGB chemistry, AGB magnitude, so do they have infrared access? So for all we could tell, there was no impact of our selection on that. And obviously, there is the issue, right, that we are doing giant stars, and we know that there is internal mixing as the giants evolve, and therefore we have to account for that, and we did account for that. Regarding the discovery of Heracles, what I can tell you is that the entire study, as all the other studies that we performed here, when it comes to this chemical tagging, they are fundamentally differential in that you take 2 samples that were selected in the same way and you compare their chemistry. Right. So the spatial distribution, the kinematics, of course, is not the same, right? But the spatial distribution of for instance, Heracles and the high alpha disk stars that live with it are the same. So we try to cover all our bases in terms of this kind of selection effect. Now, that said, the energy gap, for instance, between Heracles and Gaia Enceladus has been shown by James Lane to be partly, but not entirely, due to an apogee selection effect.
Yep.
So, yeah.
Caveats. Then, Wynn, you have a question? We can't hear you.
Oh, sorry. Can you hear me now?
Yes.
Yes.
Very nice talk, Ricardo. I have two questions. First, can you tell us a little bit more about what you believe the structure of the Heracles remnant is? For example, is it prograde or retrograde? What's its mean rotational velocity and what's its structure? And then the second question is, I mean, correct me if I'm wrong, but I think what you did was you looked at a number of two-dimensional projections of a very high dimensional data set and looked in those projected spaces for separations. And right. I was wondering whether it was possible to do the separation in the higher dimensional data space itself.
Okay, this is okay. So the first question. Let me show you here I'll share the screen again to answer the first question, and then the second question is one that is fascinating indeed. So let me see here. Where is it? Sorry. Okay. Right. So what you see here is our selection for Heracles. Okay. So the answer is the bulk motion is non-rotational. It's a hot cell population. Now, you do see here that there's if you look at the distribution, if you squint a little bit, you'll see that there is a higher component here with prograde motion, but these are most likely disk contaminants. The contamination by the metal poor thick disk is at between 22 and 40%. So the problem here is that because it's a hot component, right? Distinguishing it from the metal poor in situ population, which also is hot predominantly, right? Is difficult. So you can distinguish that from the prograde component, which is there, right? But from the rest, it's very hard. So the spatial distribution is. We would need to apply the apogee selection function and try to infer it from the data. We haven't done that yet, but that's currently in the to-do list. Now that's correct. We did look into the projections, and we did also. This is actually one of the questions that the referee asked us. Maybe you were the referee. So,
I wasn't, but I think it's an interesting question.
It is a fascinating question. And so let me show you another few projections here. What is it now? Sorry, just a second. So yeah, so we looked, for instance, at the in this case 1D projections. So let me share the screen again. Right. Right. So this is comparing the distribution of various integrals of motion, right? Action and the energy and with the in situ population, and they differ at a very high statistically significance. Here's the prograde component that I was talking about just a minute ago. Now, what we did was probably because I'm a three-dimensional person who likes to look at two-dimensional projections, right? We concluded that if there are differences in projection, they must exist as well in multi-parameter space. We did initially, when we were considering the chemistry itself, right? The chemistry is playing the fundamental role here. We did first try to implement those methods of structure finding, the off-the-shelf structure finding methods. And what we wound up concluding was that they did not offer a robust discrimination of the structures that we're looking at. Ultimately, what I'm trying to say here is that the data are not probably, without a physics-oriented eye into these differences, you cannot conclude much. I'm trying to say here, because they don't jump at the eye other than just what I'm just showing here. I don't know if I don't think I have head-on addressed your question, but it's probably in the to-do list as well.
Yeah, thank you.
Thank you.
Any more questions?
Eugene has a question.
Eugene, go for it.
Hi, Eugene.
Hi, Ricardo. I have a question about the last part of your talk, where you were showing that there is a difference between the galaxies that have bimodality versus those which haven't.
Yeah, just a second.
And can you show this slide? Because it seemed to me that you picked them up from the simulation, I believe, and it seems that they also differ quite systematically in the total stellar mass. So if you normalize the stellar mass of both things, would you still see a significant difference between them?
There is an answer to that question. When so I think this is not a problem. I just fail to recall what the correct answer is. I'm sorry, I'll have to get back to you on that because I don't recall what this is not an issue, in other words.
Because I think I've heard this statement also from other papers, but it's not transpiring from this particular plot.
Yeah, I think you have a point there. I should have. The thing is that the last time I gave this talk, I was asked that question. I had the answer, but that was over a year ago. So this is not an issue. And it is ultimately related with the Correa et al. Let me go show again. But I just don't remember exactly what that is. Let me show you again. Sorry, I have to share the screen first. Okay, you see the screen, I hope. So this Correa et al. Calculation here, which you see, they both end at the same, but I don't want to, give you a completely inaccurate answer here. So I will go back to you on this.
Okay, thank you.
I apologize for not having the answer off the top of my head.
That's okay. Then if there are no more questions, then let's thank Ricardo again for a fascinating talk.
Thank you.
We can clap, sure we can. And I suggest that you all get your favorite drink and nibble yourself because we're not allowed to provide it to you. And we see you all next week. Thanks, Ricardo.
Thank you very much. Bye-bye.